Welcome to the afternoon session of PLSS. Our next speaker is Marat Akhin. So Marat is a researcher at JetBrains, affiliated with the Kotlin language evolution team. His work centers around language design and language tooling. Today, Marat will take us inside Kotlin's ongoing evolution as it enters its second decade. Time flies. And Kotlin is a language that has been re-implemented, extended across platforms, and kept remarkably self-consistent. So let's welcome Marat.
Yes, thank you so much for having me here. I will be very short. Kotlin is a multi-platform staple-type general-purpose programming language where JetBrains is its single vendor, and we have luckily only one compiler implementation. Therefore, we actually don't need any standardization or specification. Thank you so much. Not looking forward to not seeing you at PLSS 2026. Okay, I'm just kidding. Despite us being in this lucky situation when JetBrains is a single vendor of Kotlin, and we actually do have only a single compiler implementation that we fully control, we still need some forms of standardization, and we still need language specification. And that's what I'm going to be talking about today. So the standardization in Kotlin currently mainly goes through trying to standardize to some degree, how Kotlin language features get to the language. And I'm going to take you on a short trip through the whole life cycle of a Kotlin language feature from initial idea through how the design documents look like, and we're going to peek just a bit into the iterative evolution of language features. And as an offspring of that discussion, we're going to take a look at what Kotlin language specification is about, why it's not ahead of time specification as it should be, but more pragmatically, it's just-in-time language specification. I'm going to be talking about what it is in just a moment. Very important announcement. I'm going to be talking about our experience, our kind of grains of knowledge that we've collected during the Kotlin language evolution. They might not be applicable to your specific case. So take all of them with a bit of skepticism. Always try to view them through the lens of your language platform, whatever it is that you're currently standardizing or specifying. But I think a lot of what I'm going to be talking about, it really kind of reflects and mirrors things that we've already talked about before from the great speakers that were in the first two sessions of today. So Kotlin in 30 seconds, I'm not going to be talking about how the syntax looks like. I'm not going to be talking about does it support functional programming. The most important thing that I want to focus on today is that Kotlin is a language that in a sense, has some notion of a common code. So kind of like Kotlin that you write, and you expect this to be working on all of the other different platforms. And there are a lot of platforms that Kotlin needs to target. Right now, we support compiling to JVM, including Android. We support compiling to JavaScript, to Wasm, which is not on this picture, unfortunately, because I didn't have the time to fix it. We support compiling to native, specifically to iOS and different flavors of iOS. So there's a lot of platforms that Kotlin needs to target, and that will be important for the part about standardization and specification a bit further down the line. So how does life of a feature look like in Kotlin? This is literally a screenshot of how our internal documentation talks about what should happen for the feature to get from the initial idea to being added to the language as the feature we fully support or removed. And it all begins here with a fork. We either can begin with an idea of a feature or an external feature request. You might ask, why is that? Well, the thing is that these feature seeds are importantly different. A feature request usually is external. It usually comes from the Kotlin users that we have, be it our early access preview champions or regular developers who reached out to us through some channels and said, listen, we really want Kotlin to have this. In a sense, this is a signal that there is a problem out there that people know about, and they want us to try to find a solution to it. So the problem is there. in air quotes. I'll explain why in quotes in a bit. And there might be a solution to it which you need to find. Whereas if we come with an idea of a feature, it usually comes internally from the Kotlin team or Kotlin language evolution team specifically. And like we're usually thinking about it would be great to add to Kotlin features from other languages, or we've seen a great paper from PLDI or POPL or eCoop about something really, really great that you can add to your programming language. And we're viewing a solution to something which might be a problem. And like this distinction about external and internal and about problem and solution is important because to move forward, you actually have to have a problem with good enough solution. And like that's the first kind of like the first gate watch, and Cody keeps Cody his our mascot, their mascot, like he's keeping tight look on the gate of what features get into the Kotlin. So kind of like a good feature is about combination of both. This is a problem that people care about and you should actually solve, to this is a problem which is actually solvable. Why? Because in a lot of cases, problems are not actually problems. For example, people have been bugging us about Kotlin should add union types for, I don't know, 5 years, maybe even more. Whereas when you actually ask people about what is the problem that they want to solve with union types, it turns out that they don't actually need union types. They need other features added to the language, but they don't need the full power of union types with all of the accompanying problems that union types introduce to the type system of the language. Tooling support and so on and so forth. Sometimes solutions are not actually feasible, for example, specifically for Kotlin. As an example of that, we would very much like to have full exhaustiveness checking for our kind of like pattern matching /when expressions. But like if you go for full-blown general exhaustiveness checking, that's basically a set problem. You have to add a set solver to your compiler. This is not something we really think is a good idea. And like other combinations are also possible. So for example, sometimes a good problem, it just doesn't have a good solution. Like we would like to avoid all index out of bound exceptions, but Bryce told us that it's impossible in general. And sometimes solutions, which are great, they don't target actual problems that happen in Kotlin. Like we were eyeing, for example, algebraic effect handlers and adding those to Kotlin again for several years now, but it just turns out that it doesn't fit the domain of how people usually use Kotlin, and they won't benefit enough from Kotlin adding full-blown algebraic handlers, probably just yet, but right now we're here. And like as the very, 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 very basic threshold that a feature has to jump over is there should be a lot of code or a lot of people who are saying that like we're really struggling with this. And what we do, we just take a look at the code that people write. Like this is like the first checkbox that's like one of the first checkboxes in the checklist, again, internal checklist that we have for if you are considering adding a feature, what you should do. You should take a look at, is this pattern of code that you are trying to solve, like, does it happen a lot on GitHub? Or does this pattern of code, which is problematic, happens a lot of GitHub? And like, if it's not there, then it's probably not something you should do. If we're happy with what we found on GitHub, then we implement more fine-grained analysis using custom-built compiler. And we run it on our own internal set of user projects, which include like different applications and libraries written in Kotlin across our whole ecosystem. And we'll take a look at how often this actually happens and give us more precise results. But we believe right now that it's like precise enough. Historically, we used to have our in-house, even more powerful code search tools that allowed you to search across all of GitHub. But it turned out that it's very costly to support. And like in some sense, it's too precise. The results that we get from this stage, in our experience, this was enough. So, okay, now we've kind of like checked the first box. We understand that there is a problem that people struggle with, at least formally. So there is code out there in enough capacity, in enough quantities that struggle with some problem. Then we try to kind of like compress everything that we know about this problem into a design document. And design documents in Kotlin are known as keeps, short for Kotlin evolution and enhancement process. They live in this repository. You're free to go there and try to read them. And it basically contains everything around design of Kotlin, from draft design nodes of something we believe might be interesting within the next 5 years of evolution, to in-flight development of different proposals, to a list of things that we tried and rejected, and we tried and accepted. A very important thing here is that every keep must have a driver from the Kotlin team. Previously, we tried to accept features from outside contributors, but it just doesn't work. It doesn't work mainly for 3 different reasons. Reason number 1, for an external contributor, it's very difficult to go in depth enough because they just don't understand enough about Kotlin, about ecosystem, and about how our processes work. The second reason is that we found out that in a lot of cases, people are biased towards this is what you should add because my code would benefit from it. That's kind of like goes in line to a point that that was made before about saying no. So kind of like people love pushing their solutions that work for their code onto you as a language designer. And like to avoid that, we're just saying that everything comes internally. And it's very hard actually to write a good enough keep if you're not getting paid for it. It's our job to do that. So that's why everything that we do, it must have a driver from the Kotlin team. Like if you actually think that you have something interesting and you want to reach out to us, then you have channels through which you can do this. And if we think that this is a problem that is worth investigating, we will pick it up and we will begin going through the process that I'm currently explaining to you. Like if you go through the anatomy of a keep, this is just like a table of contents of one of the keeps, I think, on guards. Yeah, and like it roughly follows the same overall structure that it talks about. It talks about the problem, first and foremost, about the motivation, why this feature is important, and about these use cases, these code samples that the feature is intended to cover, intended to fix. Then it talks about the solution, about the feature design from the external developer perspective, from the Kotlin user perspective. And it also goes in depth about how you actually implement this feature, what is needed to what you need to think about, how it interacts with other different things in Kotlin, and so on and so forth. And it also discusses the risks and problems that can happen. And there we go deeper into trying to understand if this problem actually exists, if this problem actually is important. First, we kind of like push it through the infamous Toyota's 5 rule, just because in a lot of cases, when you begin asking why you think this is a problem, why you think this should be changed, it turns out that the answer is it shouldn't, and there are other ways you solve the problem. By example, by giving people better documentation about how they should use the things that they're using incorrectly in a proper fashion, or by giving people some other abilities to do this. I will talk about those in a moment. Like if you pass the why, you really think that the feature should be added, then you begin crawling out of the minus 100 points pit hole. Basically, we always try to challenge adding the feature, because the best feature actually is the feature that you never added to the language. It means that like you don't have problems supporting it, thinking about it. The people don't need to teach themselves anything new about your language. And like we're really asking a lot of questions about, is this actually needed? Do you really need to change the language? Is there nothing else that people can do within the existing capabilities of Kotlin that will fix their problem? If all of those things click, then we're taking a look like, is this a Kotlin enough problem? Because in Kotlin, unlike in many other languages, we have additional tools which we can use to solve problems. For example, we have wide history of solving problems, not by adding features to the language, but by adding new libraries or new capabilities to the standard library of Kotlin. We have pretty extensive Kotlin compiler plugin, which we're actively working on stabilizing, you can say standardizing also, but that's a topic for another talk. And like another close to unique capability of Kotlin is that we're very closely coupled to our IDEs. And in a lot of cases, things that you can solve by adding a feature to the language, you can better solve just by giving people better IDE support for what they want to do. So if we think that this is a problem, then we begin taking a look at, is there a possible solution for this thing? And here, like, we understand that we're not geniuses. We cannot think of everything by ourselves. We're taking a look at everything that's happening around, at what's happening at other languages, what's happening in PL research. We're taking a look at like state-of-the-art publications from POPL, PLTI, eCoop, FSC, and other conferences, trying to see if there anything interesting as a solution to the problem that we understand is important. And then we're trying to see, can we implement actually what we want? Because in some cases, the compiler limitations, the limitations of implementation of our compiler doesn't allow us to implement what we actually want. And like, if there is a solution, then the solution should also answer yes to the question, does it help reading the code? And is the mental model of what we're adding to the language easy to explain? So this is something very important that we always try to preserve. And we're trying to make it so that if you add a feature, then basically you don't need to teach people a lot about this thing because the code explains itself in a sense. And then we go to the rigs part of Keep. We try to understand whether the feature that we are adding has some unintended consequences, whether it will break something from the backwards compatibility perspective, and how it interacts with existing features, and how we'll go forward with teaching and migrating the users to this new feature. So, like, if you slice Keep in a bit of a different way, then again, the beginning of the Keep kind of talks about the external view on the feature. So how people read about the feature, how they will use it, how will the code look like that the feature allows people to write or disallows people to write incorrect code. And the second part, the second slice is kind of like about internal things. It tries to ask you as an implementer and designer of the language, how you answer all of those complicated questions about the interplay of internal things within the feature. And it's actually kind of like all about the dependencies, because you want to add a feature to kind of like this huge blob of complicated subsystems within your compiler, and you want to understand what are the dependencies of the feature, what are the other things in the compiler and in the design of your language that this feature touches upon and potentially changes. And actually here, it's not about dependencies. First, it's about the language, because if you want to talk about those things, you need a common language to quote unquote standardize a language feature, because some person might be talking about function default arguments. Another person might be arguing with the first one about, no, like optional parameters should like work differently. It's a completely different thing. Whereas they're actually using different names for the same concept just because they don't know better. They don't have this common language. And you need to standardize this language to talk about a language feature. And if you do it enough, then you end up with a language specification. And here we go to this offshoot of what I mean by when I say that Kotlin has a just-in-time specification and how the specification for Kotlin actually looks like. So Kotlin language specification lives here. It's currently 310 pages of formal, just enough prose of how Kotlin core should work. And Kotlin core is precisely, as I said, this platform agnostic parts of Kotlin, the core things in the language that should work the same way. Terms and conditions apply, irregardless of what is the platform you're compiling to, be it JVM, JavaScript, WASM, or native, type resolution, overload resolution, inference, they should work the same way. Otherwise, you are having problems. A little bit of history of how the specification actually came to be. Kotlin was originally created. The idea for Kotlin happened in 2010. The first commits, I think, were in 2011. And like 5 or 6 years later, in 2016, Kotlin 1.0 was released. In 2018, and at the time, specification was there, but it was mostly just a collection of technical documentations about subsystems that people cared about. And there were a lot of things that were missing. In a sense, it was like even more just in time than currently. In 2018, Kotlin 1.3 was being released, and two important processes began there. First, we began the reimplementation of the type system, also known as new inference. And we also began reimplementation of the whole front end, also known as K2. And then over the years, we actually finished both of the reimplementations. And when we began this, we understood that, well, actually now we need some specification to guide this reimplementation process, because otherwise we're, in a sense, flying blind. So, and within the spectrum of what you can actually write to explain how your compiler should work, we ended up in this heavy prose-like formal just enough language specification, not going forward as WebAssembly did, and like your guys, you're great. Like I really love the talk on WebAssembly. We didn't go there, but we also didn't go like higher and just going with like very prose like very user-facing language reference. Why is that? Well, you need a formal specification, and I think like that's the point that I already mentioned, when you have more than one compiler for your language, because in that case you definitely need an independent source of truth that people can agree on. And like in a lot of cases that they don't only need this again written, but they also need some kind of executable behavior that would be like ideal. Or if the cost of a breaking change is too high, if you're working on a compiler for like safety or mission critical systems. Kotlin is not in this situation. Kotlin is in a situation when you actually re-implementing large parts of the compiler. So you're kind of like having not two parallel compilers, but two compilers, but sequentially. And in that case, you do need some kind of formal, just enough specification so that you can talk in the same language within your team about different subsystems, or that you need to support new tooling for the language. And you also need this formal, just enough specification, and you are not really happy with just having language reference. It can be a really very good language reference, but like if your language is complicated, if the compiler is very smart, if a lot of the things in your language are implicit, and that's precisely the situation that Kotlin ended up at. So that's why when we have the need for a proper specification, and when you write it, well, of course, you always write the specification before you write the implementation, but if you have these checkboxes checked, and we're lucky enough to check all three, if you already have an implementation, it's too late. You have to write the specification after you're already bound by the specification, by the implementation, sorry, and you actually want to preserve backwards compatibility. Because in the ideal world, and there were like multiple times over the specification of Kotlin when we really wanted to say that the compiler actually needs to behave like this, because this is what makes the most sense from the specification point of view and from the language design point of view, but we cannot break it just because we will break our users, and that is something unacceptable. And that's why going for a full-blown ahead of time specification, it wasn't feasible. So we went for an approach which I currently like to call just-in-time specification, when you basically select the things that you consider important, you specify those, and you omit the rest. You can specify only the parts that you need to talk about the new feature, or you need to compare the old and the new implementation, or you may find some other reason not to write full-blown specification for everything. And that allows you to talk about the important parts for the processes that happen during your language evolution, in our case, re-implementation of the compiler, and introduction of new features, and do not spend resources on other things. So like, we like it because it's super pragmatic. You specify what you need, you don't specify what you don't need. It ends up that your specification is smaller because like this is, for example, a just-in-time specification for the changes of overload resolution for one of the features. Again, screenshot from the keep. Like, it's easier to think about for people who are reading this, because this is read not only by language designers and specification writers, but also by compiler, developer, by implementers. And for them, they appreciate these pros like more. And it's just faster and cheaper to write, because we can write a great specification. It's gonna probably cost quite a bit, whereas we could spend these resources more efficiently on other activities to improve the quality of our language and our compiler. Just specification is not perfect, because like, it requires discipline. And there are some situations when we didn't understand, because nobody told us, that we actually need some parts of the compiler specified, because teams didn't understand that they need to come to us and tell us that this is something that we need. We're roughing it out, like we're fixing these problems right now. But like, it does require a lot of discipline, because it's basically, it changes from the push approach, when you're pushing ahead of time fully written specification onto implementers, to the pull approach, where you say, listen, if you care about some parts of the compiler and some parts of the language, tell us what you need specified and we'll work on that. It also can miss things, because you're kind of like picking the right parts and hoping to always pick the right and never miss something. And sometimes it's not enough. For example, if you're doing something completely new, completely disconnected from everything else in the compiler, then you don't have anything to bootstrap you into adding parts to existing specification. Or if you have a lot of external dependencies, and this is actually our most important current problem, the problem that we are hoping to solve going forward. So as I said, we have a specification for Kotlin core, for platform agnostic part of Kotlin. And right now we understand that we need to also specify how we work on different platforms, because right now with Kotlin multi-platform being a thing which is used more and more, we need to solve the differences in very complicated cases that can happen when code across platforms needs to interoperate. And we'll be working on that going forward. I don't know what's the good solution. I don't know how we're going to fix this, but this is something that we're going to be doing. So back to the life of the feature. We know we have a problem. We have written the design document that covers the problem and doubles down on this as a problem. We found the possible design of the solution, and we've written the just-in-time specification that covers just enough to talk precisely about this solution and this feature in general, but we didn't spend extra resources on writing more. So then we just go and ship the feature forward, and like, there are different levels of feature stability that the feature always goes through. It begins with experimental, then goes to alpha, beta, and after these are pre-stable features, and then goes to stable when everything is alive and well. And like, you would assume that these stages mean that you can break things easily, and only at stable you really say this is really, really stable. Unfortunately, no. Like, Huron's law is a thing. As it turns out, if there is a Kotlin feature which is hidden, which is never advertised, which is under several compiler flags and several internal annotations that you have to jump through several hoops to actually use in your code, people will find it probably within the first month that the feature is in the compiler, and they will use it, and they will depend on the behavior. And only after Kotlin 2.0, we actually found the courage to begin changing or even dropping completely pre-stable features. That is, like, the reason for that is very simple. Before that, we really cared about our users. We wanted them to be happy, and we preserved backwards compatibility, even sacrificing, again, some some purity of language design in the language, just because it was important for us to get user attention. And that is something that a lot of the languages don't take a look at very much, but we did. Since Kotlin 2.0 released, we understood that we finally are big enough in our user base that we can begin breaking things, of course, providing migration support to the users to fix old design depths and features that should have been removed from the language way, way before. So when you drop a feature, like very, very shortly, you don't drop a feature if it's a good feature. First and foremost, the feature should be useful to us. We always battle test it first in the compiler, in our libraries, in our IDEs. And then we push it out and advertise it across our, again, EAP champions and our more advanced power users. And if people write less code as a result of the feature, the code is easier to understand, and people write less error-prone code, then it's a good feature. We probably will keep it. But sometimes it happens that the feature creates unexpected problems, it creates bugs, it breaks other features, or it turns out that the solution actually fails to solve the original problem because we made a mistake during all of the stages of preliminary analysis. In that case, we're thinking about removing a feature. Bear with me for just several minutes more. So what happens if in this process, at any point, there is a tie? What I mean is that there are several good or bad, equally good or equally bad design decisions for a feature at any point in the process. I would love to tell you about that democracy is great in language design, that committees are awesome, and you should always gather a bunch of smart people and try to come up to a majority decision on how things should look like. In our experience, that's not the case, and we have a little language designer for a reason. We found out that first, democracy has the same success rate as just pick any solution and go forward. And second, we didn't manage to find a good framework to objectively compare different feature designs because they're subjective almost by definition. So if there is a tie, this guy, Michael Zarashinsky, the language designer, he has the final say of if the feature goes forward or not. Why does this work? Well, because we iterate. Because after all of this is said and done, we implemented the feature, we go forward, we try it out, we see what works, what doesn't work, and we iterate. And that's what allows us to just make a decision, stick to it, and it will fix itself later during the iteration process. So that's basically it. The standardization for Kotlin language features goes through trying to understand whether this is a feature for an existing problem that has a potentially good solution that fits Kotlin design, that fits Kotlin design, that it's implementable, and then we iterate trying to either accept the feature or deprecate it and then remove it from the language. And behind the scenes, writing just enough of the specification to cover the important dependencies within this feature to existing parts of the compiler implementation or the language. It kind of like it helps behind the scenes to keep this whole process going forward. Before I conclude, I would very much like to ask people, let's try to contribute and collaborate by sharing problems, because like we're very interested to hearing what other people believe are important problems in language design and how, for example, you collect the user pain points and maybe even share solutions. Where are you looking for those? How do you compare a feature between languages? How do you check that a feature you want to add to the language actually clicks for your language? So that's it for me. If you like to talk more, then I'm here till the end of PLSS, and these are my and Michael's emails. Feel free to drop us a line if you're interested. Thank you so much for listening.
Thank you very much. Thank you. And do we have time for a question? Yep.
Thank you very much for the presentation.
Yeah.
Thank you very much for the talk. I'm not that much familiar with the kind of like language evolution process like from Kotlin. Is this something that is community driven or like solely like steered by JetBrains, like by the Kotlin team there?
As I said, yes, because everything happens through the key process. And the key process is driven by the Kotlin team. We're actively listening to the community, but in the end, the say of what is added or not added to the language, that we are responsible for language maintenance. We're responsible for good and bad things in Kotlin. So that's why it's driven by Kotlin, by JetBrains.
Mm-hmm. All right, and then I also have a follow-up that kind of relates to it. It keep that as a context, and as well as, for example, you started out the talk with you have the luxury of just having one compiler implementation, for example. So personally, I think those might be very correlated to each other, JetBrains driving the process and being the decision maker essentially, and also leading the project and the compiler.
Yes.
So you presented the practical just-in-time approach of specifying things whenever you need to change them. I think just-in-time is very fitting because you can contrast that with ahead-of-time compilation or ahead-of-time specification of the language. And I think I'm curious on your take, because I think it essentially shifts the burden on just-in-time specification shifts the burden on the feature contributor essentially, because there might be some things that are unspecified, and in order to make it change, you might need to deal with catching up or with a lot of legacy of specifying the behavior first before being able to contribute the feature. So I'm curious on how you see that, or if you perceive that as blocking, for example, for making some contributions.
Yeah, that is entirely correct, and that mirrors the point that I think Adam did on APL doesn't have a specification for what an expression is. That's a problem. So yeah, we do encounter these problems from time to time, but for the most part, we covered just enough of the things that most of the features care about, so we don't hit those blind spots as often as it might seem we do. When we hit those, then we go there and either fix them immediately if we understand that it's a blocker, or we just write it down that this is something we should specify going forward, and we keep the old of implementation is the ultimate specification approach. But to answer the original question, yes, you are correct that in some sense it puts more responsibilities on the implementers of features, because in Kotlin, in the end, the ideal Kotlin specification is the Kotlin compiler implementation, because there's only a single one.
Okay, quick one. How can you be sure that there's just one Kotlin compiler implementation out there?
Just because I'm not sure that there is people insane enough to try to implement everything that we have in Kotlin. That's half jokingly, half serious answer, but I have a feeling that if there were second implementation, we would know about it. We know about tooling around Kotlin, and we can talk offline about this a bit more, but there's definitely no second Kotlin compiler implementation that I know of. Not that I know of, there is no second compiler implementation at all.
All right. Yeah, I was referring mostly to there might be very complex things that you want to do at compile time, for example, differential automated programming, for example. And so I'm wondering if having a lack of specification in some parts might also hinder, for example, proprietary vendors or other people doing research or starting up on those projects themselves. So it might not be that all of those projects are openly available, but who knows, maybe there's 5 Kotlin compilers out there in the world somewhere.
There might be forks. And again, we can talk offline. I don't want to take more time.
Yeah, sure. Yeah. Thank you very much.
Julia?
Yeah, I wanted to pick up on the rather nice joke that you opened with, that, we only have a single vendor and we don't really have a specification. So that's the end of the talk. That was a great opening. I think your talk touched on a lot of interesting issues that this workshop wants to tackle, because there's also a difference, of course, between specification and standardization. And standardization becomes really important when we think about like vendors agreeing on how a given feature is going to work in every single version of an implementation. And this is definitely something that Adam mentioned APL is running into because of the divergence between multiple different vendors. However, one vendor in that case has definitely taken the lead. So I'm really looking forward to Karta's talk so that we can hear more about this space. But your talk is really also looking at how specification enables collaboration, especially with users of a language. So for example, my experiences in JavaScript and also a little bit in the WebAssembly space, we have vendor discussions, and the vendor discussions definitely guide how we design the language as well. But then there's also the discussion with the community, which you mentioned, and we have a very similar process, which I think Michael Ficarra will talk about in a moment. So I just wanted to point out that this talk is very interesting in terms of contextualizing how standardization, specification specifically can assist in the design of a programming language, especially a modularly designed language. And I think these technologies and tools that are coming from the industry space may be very useful in pushing that forward. So,
yeah. So like a minor data point here, during Kotlin Conf this year, several people came to us and said that specification gives them precisely this language to explain complicated features in Kotlin to their colleagues and like push for Kotlin adoption, for example. So yeah, that's kind of like to reinforce the point that you made.
Yeah, and I think, in fact, this is really important about specifications as documentation techniques. We see this also in WebAssembly, this fantastic project that we had presented by Andreas at the very beginning, where we have multiple representations of the same specification so that it can target different kinds of groups. So, for example, a natural language specification is much more useful to implementers. And these tools might have further implications in other spaces, which I think is very interesting. But I think we will probably wrap up here on Kotlin and move on to our next talk. Is that right, Michael?
Let's thank Marat again.